Good evening, good day. So let's start our evening session. The first speaker is Elias Kiritsis. He will tell us about graphic ergo flows on curved manifolds and F-theorems. Please, 45 minutes.
Thank you, Irina. Thank you and all the organizers for setting up this remote meeting. Hi to all the friends I see in the audience. I hope everybody is safe and healthy. So what I'm planning to tell you in this talk is on some recent work we've been done in trying to understand in more detail holographic RG flows, especially when it concerns quantum field theories that live on curved manifolds, and how this knowledge can be used to refine or describe newer theorems. I should say that if you have a question, please just open your mic and ask a question. So let me make clear that what we'll be addressing in this talk is unitary Lorentz invariant quantum field theories. As you all know, the Wilsonian paradigm builds on the quantum field theory landscape, starting from conformal field theories or scale invariant theories, and then the rest of landscape is filled by renormalization group flows. As also is well known, the Wilsonian renormalization group is controlled by first order flow equations of the form derivatives of the couplings with respect to the log of the renormalization group scale is equal to beta functions. And although the basic rules of the flows are well known since a long time, the global structure of the flows is known mostly for weakly coupled quantum field theories. We've been studying this for 50 years at least, and still there are many aspects of quantum field theory renormalization group flows that are still not understood. In particular, it is not known if endpoints of renormalization group flows in 4 dimensions are fixed points or whether they include other exotic possibilities like limit cycles or chaotic behavior. This is correlated with the potential symmetry of scale invariant theories. We know that if a scale invariant theory is also conformally invariant, then this excludes the exotic possibilities. And in 4 dimension, we know also that every scale invariant relativistic unitary quantum field theory is also conformally invariant. However, in 4 dimensions, although this issue has been analyzed very intensively recently, there are still loopholes in the general argument. So the goals I will set up here and in my work, but also in this presentation, is to use holographic theories, which means large and strong coupling theories at strong coupling, in order to investigate renormalization group flows beyond weak coupling. And I will do that by first building an understanding of the general structure of holographic renormalization group flows of quantum field theories on flat space, then try to build an understanding of the general structure of holographic RG flows of quantum field theories on curved spaces, like spheres, for example, and then use this knowledge to revisit C and F functions in 3 and more dimensions. So I will be using for both simplicity and clarity a bulk holographic theory, a gravitational theory that will contain only the metric and a single scalar field. This is usually called Einstein-dilaton gravity. So the metric will be dual, of course, to the stress tensor of the quantum field theory, and the scalar field will be dual to a scalar operator O of the dual quantum field theory that would be driving the flow. The 2 derivative action after field redefinitions, the most general one can write, is written here, and it involves, of course, the Einstein term, a canonical kinetic term for the dilaton, and a potential for a dilaton. I will assume, as we know from string theory examples, that the potential for the dilaton is analytic everywhere except possibly at the boundaries of its space, which in this particular normalization are at phi equals plus or minus infinity. I will also be considering the ADS regime, that is, I will consider the potential to be negative, or if you wish, I will be working in regions of field space for which the potential is negative. And I will be looking for solutions with four-dimensional Poincare invariance, so that the ansatz for the metric will have the standard form. U is the holographic coordinate, and e to the a is the scale factor of the transverse slice metric, and phi, the scalar, would be a function of the holographic coordinate. This type of symmetry corresponds to what we would expect for the vacuum saddle point solutions of the dual theory. And in this context, the analog of the renormalization group scale is essentially proportional to the scale factor of the bulk metric, which near the boundary, of course, takes the familiar ADS form. And in a sense, the function A is essentially the logarithm of the scale factor. If the scalar is constant, the solution will correspond to the vacuum solution of, if phi is not constant, then the solution will correspond to the vacuum solution of an renormalization group flow that is driven by the operator O, which is dual to the field phi. Now, the bulk Einstein and scalar equations are quite simple, and most of you must have seen them many times. I've written them here, and essentially, out of the three equations, two of them are independent. There is one second-order equation, either this one or this one, and there is a first-order equation, and they have three integration constants that you can take them to be two integration constants for the dilaton equation and one integration constant for the Hubble equation. So if we solve, for example, near an ADS boundary, then the scalar has the familiar form with the leading and the subleading linearly independent solutions, and the two integration constants phi 0 and phi 1, as you all know, correspond. Phi 0 corresponds to the to the coupling constant, the ultraviolet coupling constant of the quantum field theory, whereas phi 1 is essentially proportional to the vacuum expectation value of the operator that's dual to the scalar. Of course, since the beginning, we had an obvious and interesting question, how second-order field equations in gravity can give us first-order Wilsonian renormalization group equations, but as we will see, and as most of you know, this is to a certain degree understood until now. And a key ingredient in this is that we understand phi as a function of the radial coordinate as the analog of the running coupling constant of the dual quantum field theory. So to match second-order equations to first-order equations, we can use the so-called first-order formalism, where we introduced a function which is traditionally called the superpotential, although there is no supersymmetry here. This is generic. It's defined in a sense as to be essentially a dot up to a convenient normalization, and we think of it as a function of phi that parameterizes also the non-trivial flow. So if you define W from this equation, then one of the two Einstein equations tells us that phi dot is proportional to the derivative of W with respect to phi. Primes stand for derivatives with respect to phi. Dots stand with derivatives with respect to the radial coordinate. And then the third gravitational equation, in fact, boils down to this first-order nonlinear differential equation that relates this function W, the superpotential, to the potential, to the dilaton potential that exists in the Lagrangian. So this is old knowledge. Now, it is important to understand a little bit how it works with integration constants. The original system had three integration constants. And in fact, here we have two integration constants for the equations for A dot and phi dot. And we have one more integration constant here in the first order equation. So for a given potential and for a given theory, the equation for the superpotential has a one parameter family of solutions, and that matches, of course, what we expect from the original system. So there is one-to-one correspondence between the two systems. Now, if we integrate these first order equations for phi and A, the integration constant, which is A0 and phi 0, essentially are interpreted as couplings of the dual quantum field theory. We can define the analog of the beta function here, the holographic beta function, to be essentially d phi dA. Phi stands for the coupling constant, A, as we said, stands for logarithm of mu. So this is phi dot over A dot. And then by using the first order equations we wrote here and by taking the ratio, we find that this is essentially up to a constant W prime over W. And this is more or less the holographic beta function. The third integration constant, which let's say is phi 1 and it's hidden inside of W, controls essentially the vacuum expectation value of the operator O. And here comes the very important property of holographic solutions, that we have to ask for global regularity. And global regularity, as you all know, fixes the value of the subleading solution for the dilaton, let's say, which controls the VEV in terms of the other parameters of the theory, like coupling constants. And then eventually we end up only with independent parameters that refer to the parameters of the quantum field theory. So the conclusion of this that most of you know is that renormalization group flows are in one-to-one correspondence with the solutions of the superpotential equation that I wrote here and connects the superpotential to the potential. And then the superpotential determines the flow, the first equations of the flow, and the beta function. So regularity in the bulk out of all the solutions of the superpotential equation picks only the ones that give a regular solution, and typically in generic cases this is unique. So there will be a unique solution to the W equation that will give a regular bulk solution, and therefore if the superpotential equation has a unique regular solution, then the holographic RG flows look essentially like first order Wilsonian renormalization group flows. And this more or less tells us that there is a map between precisely what we've learned in graduate school for quantum field theory and what we are doing in terms of renormalization group flows in holographic theories. However, there are subtleties to this, and I would like to get to them before going further. Let me, first of all, remind you a few properties of this superpotential. First of all, if you remember the equation, there is a symmetry to changing the sign of W and also changing the direction of the flow, because if you change the sign of W, then you will have to change the sign of U here so that everything is consistent. So, and this is a symmetry, and by using this symmetry, we can always take the superpotential to be positive. The other thing is that if you solve the superpotential equation, let me go back to it, this one for W in terms of V and W prime, and because W prime square is positive, you derive an inequality for W which says that it's always bigger or equal to the square root of minus a constant times V, and remember that V is always negative in our discussion. Now, this combination, I call it B of phi. It will appear in many plots below, so I will ask you to please remember it, because it's an absolute lower bound for any solution for the superpotential. Moreover, one can prove immediately the analog of the C theorem, the holographic C theorem, which says that the derivative of W with respect to the radial coordinate, if I do the chain rule, is dW d phi, which is W prime, which is equal to phi dot, and this is phi dot, or it's W prime square, and this is always non-negative. So this is automatic. And the other thing that you can derive by manipulating the equations and studying them is that the only singular flows that you will find to this system of Einstein equations are those that add up with the scalar running off to infinity. If the scalar always remain finite, all the flows are finite. Therefore, all regular solutions to the equations are flows that start from an extremum of a potential and end up in another extremum for finite values of phi. So these are general properties. So let me remind you a couple of things about the extrema, because I would like to define an important quantity that I will be using later on. So if I have solutions with constant scalar, then I have to always be at the extreme of the potential, and the extreme of the potential describe holographic conformal field theories. Now, let me describe the solution for the superpotential near a maximum of the potential. So I parameterize the potential, I put the maximum at phi equals 0, I set the dimension of the boundary to be equal to 4, I expand the potential near the boundary, and as you all know, we can connect the mass parameter here with the dimension of the perturbing operator. And then one can see that this solution describes a region near a UV fixed point, which is perturbed by a relevant operator of dimension delta, which is smaller or equal to 4. And the general structure of the solution for W has two pieces. It has a perturbative piece, which is a power series in phi, and a non-perturbative piece, which is a trans series in powers of phi to the 4 over delta minus, or 4 minus delta, in 4 dimensions. So I write it here. You have a power series that I wrote in this first piece, and then there is an integration constant to the superpotential equation that I call C, which multiplies this leading power, and then of course this is a trans series, that is, this is multiplied by a power series in phi, and then there is square of this times another series, etc. And as most of you know, C is essentially determining, this is first of all the one that is generating the linearly dependent solution in the equations for phi, and it's determining the VED of the dual operator with this particular formula. That is, the VEV is this dimensionless parameter C times the relevant coupling to the appropriate power. And if we use this formula to compute the beta function, then the beta function has the structure that we expect in perturbative quantum field theory, the leading classical piece, then you have the various quantum pieces, this is the perturbative part, but then the extra parameters that are proportional to the VEV give, in fact, non-perturbative contributions to the beta function. Maxima always describe ultraviolet conformal field theories, but minima generically describe infrared CFTs, but there are exceptions, and we will see them later. So let me describe quickly the flows you've mostly seen, which are the vanilla holographic renormalization group flows. What I'm plotting here is the superpotential as a function of phi, and the blue function that you will see in all the graphs I'm showing you is the lower bound for W, B of phi. And because B is proportional to the square root of minus V, the maxima of B are minima of the potential, that's why I call this IR, and the minima of B are maxima of the potential, that's why I call this point UV. And the generic vanilla flow starts from a UV maximum of the potential, and there's flows to the nearby minimum of the potential on both sides. And if this was the global structure for all the flows, then projecting it into the one-dimensional line of coupling constant space, we will have the picture that we know from quantum field theory, in which you have alternating UV and IR fixed points on a real line. However, it turns out that the real story is a little bit more complicated. These are the generic flows, but there is more. The first thing that can happen is what we call bounces, for lack of a better name. Now, what this happens is that sometimes W can reach the boundary region. This is a point where W prime vanishes at a generic point, not at the critical value of the potential. In that case, you can show that it develops a non-analyticity. It goes, if phi b is this point, then it goes as phi minus phi b to the 3/2, so its second derivative basically blows up there. And in fact, what happens is that you have a solution that arrives here and stops, and another solution that leaves from here on this direction. There are always two solutions corresponding to the two signs of W prime. Now, in such places, although W is singular, in fact, the flow is perfectly regular. In fact, the full solution, both the geometry and the scalar field are regular. The only special thing that happens since phi dot prime is 0 exactly at that point, and then the mapping between the first and the second order system breaks down. You can check that all bulk curvature invariants are regular at the bounds, but if you compute the beta function, you find that it has a branch cut singularity at the bounds. It goes as the square root of phi minus phi b. Therefore, the beta function in this case is patchwise defined, and it has a branch cut at the bounds. What this says is that the beta function vanishes at the bounds, but the flow is not stopping there, and that's where you see the essence of the second order nature of the gravity equations. this is certainly non-perturbative behavior. And it was precisely such behavior that some time ago was conjectured that could lead to limit cycles, although the C theorem is not violated. And indeed, in fact, in this case, you can easily check that W always increases despite the presence of the bound in agreement with the holographic C theorem. In field theory terms, what happens in such a bounce is that the coupling constant along a flow changes direction. That is, it increases and then suddenly turns around and decreases without the flow stopping. Of course, this can never happen in a first order flow. It is also easy to show in this case that although the flow can go back and forth several times, you cannot have limit cycles, in fact, in theories with holographic duals. Let me show you a few other exotic possibilities. For example, you can have a flow which connects a minimum of a potential with another minimum of the potential, which are maxima, of course, of the function B. And therefore, you can flow from this minimum, which serves now, although it's a minimum of the potential, it serves as a UV fixed point, to this minimum. And if you look at your solution, you realize that this is a flow where the driving coupling constant is 0, but the flow is driven only by the vacuum expectation value of an irrelevant operator. And also what you can show in such cases is that there is always a moduli space in such a case. That is, the vacuum expectation value can be anything you like. Now, this doesn't happen generically. In fact, for this to happen, you have to have a very special potential. But the same phenomenon, of course, is something we know happens in quantum field theory. For example, probably the best known example is n=1 super QCD in the regime of flavor where it has a baryonic branch. And there we know that it has a baryonic moduli space. The baryonic operators are irrelevant operators. Their moduli, you can turn vacuum excitation values in them. And in fact, these flows were studied later by Aharoni. So you can also find absolutely regular flows that bounce, and in fact, they can bounce several times. Here I have an example of a numerical renormalization group flow that starts from this UV fixed point, ends up at this IR fixed point, and then bounces back and forth a few times before it reaches here. Since it starts and ends at finite values of I, this is a perfectly regular solution. There are more exotic possibilities. In this plot, what I have is, again, this is the function B. These minima of B are two maxima of the potential that corresponds to UV fixed points. And these maxima of B are minima of the potential, so they are potential IR fixed points. Now, in this example, there is a regular solution that starts from UV1, flows, skips the next fixed point, and flows to IR2. But there is also a flow that starts at UV1 and ends up at the nearby fixed point. Now, both of these flows have the same coupling constant, but they have different vacuum expectation values, and they lead both of them to regular flows. In this example, so in a sense, you can think of them as two different saddle points of the theory UV1 perturbed by this particular scalar operator. And because there are two different saddle points, you can ask the question, which one has the lowest free energy? And you can always prove that the flow that goes farther down in field space, in this particular case, that means it has the lowest value of the A function in 4 dimensions, which is the one that goes farther here, this one, is always dominating. The other thing you can see in this case is that if you look at this ultraviolet fixed point, if you perturb with a coupling in this direction, you flow to this infrared fixed point, and this is a standard vanilla flow. But if you try to perturb the theory on the other direction, there is no regular flow. And the way you understand there is no regular flow is that you can prove that in every infrared fixed point, every minimum of the potential on each side, there is only a unique regular solution that arrives. This unique regular solution is this one, and therefore there is no other one. In fact, this is an example, of course, that we know from quantum field theory. If you take Yang-Mills theory, the perturbing coupling is 1 over g squared, and we know that the theory exists for g squared positive. but does not exist for G square negative. The analogous statement here is precisely this behavior. So let me summarize so far what we found, and this applies to holographic quantum field theories that are defined on flat space. So we found that holographic RG flows mostly look like standard regular QFT renormalization group flows, but the holographic beta functions contains non-analytic and therefore non-perturbative contributions. We found that there are RG flows which have beta functions with branch cuts, and in this case, the flow direction changes without stopping. We found that the holographic C theorem is always valid, and we found that there are flows that skip nearby fixed points. So now I would like to come and study the renormalization group flows of holographic theories when you put now the quantum field theory on curved manifolds. There are many reasons, in fact, to be interested in quantum field theory over curved manifolds. I mention here a few. First of all, compact manifolds like spheres are important if you want to regularize massless theories or conformal field theories in the IR, if you want to compute, for example, data like indices. Quantum field theory on de Sitter manifolds is interesting because of the fact that we think we live in a patch of almost de Sitter space. As we will see in a moment, holography predicts that a quantum field theory on a static patch of de Sitter without reference in principle to gravity has a partition function that is thermal. Also, the induced effective gravitational action as a function of curvature that we can compute in holographic theories can serve as a Halter-Hawking wave functional for 3 metrics. And in this way, ADS-CFT can provide concrete quantitative wave functions that can depend on the cosmological constant and the 3 geometry. Curvature, although it's UV irrelevant, is infrared relevant and can change importantly the infrared structure of a given theory. And in fact, one can find examples of quantum phase transition that are driven, let's say, by the curvature of S4. We will find also examples of moduli spaces that exist only at finite curvature, but not at zero curvature. And most importantly, at least for the purposes of this talk, it turns out that controlling such renormalization group flows at finite curvature is a useful tool in analyzing sphere partition functions and their relationship to F-theorems. And then finally, one can use this knowledge to provide concrete checks on claims that back reaction to the cosmological constant in de Sitter space can be important. So the setup is similar to what I used for flat space. My ansatz now, I will be using the same bulk gravitational theory, Einstein-Dilaton gravity, and the ansatz now for my bulk solution is the same ansatz, but now the slices have a metric, which is zeta mu, that now I take it, which is also the boundary metric, I'll take it to be a metric of constant curvature. The scale factor is still there, the scalar is still there, and these are functions of the radial coordinate. Z mu is a constant curvature metric, and this class includes also boundary metrics that contain the maximal symmetric manifolds like the sphere, the Sitter space, or Euclidean or Minkowski signature, and the de Sitter space. So if I solve my equations with this ansatz, essentially I am considering RG flows of strongly coupled holographic quantum field theories on the appropriate curved manifolds. So as I said, my bulk theory will remain the same. And now I have to remember that my renormalization group flow, and therefore my quantum field theory, has 2 parameters or couplings, if you wish, that control the physics. One was as before, it's phi 0, the source of the scalar field, which corresponds also to the ultraviolet coupling constant associated to the scalar operator and perturbing the theory. However, now I have another scale that is important, and this is the scale of the curvature of the manifold I put the quantum field theory on. And now you can combine the 2 scales together into a dimensionless number that from now on I will write as script R. And it's basically the appropriate dimensionless ratio of the two scales. Now, this dimensionless number, if I take it to go to 0, essentially is going to the 0 curvature limit, in which I probe the full original theory in flat space, except possibly, if R is very small, of a small infrared region. But as R becomes larger, the curvature becomes larger. And as you know, if the curvature is positive, as the curvature becomes larger, the gap of the theory becomes larger. And then slowly the theory is basically moving to the ultraviolet. This is, of course, an intuition because the gap becomes large. This is an intuition we have already from quantum field theory, and we will see the same thing happening in the holographic theory. The important message, however, here is that this dimensionless parameter is a parameter that if you vary it from 0 to infinity, you interpolate between the ultraviolet and the infrared of the quantum field theory. So again, you can map the bulk equations that I haven't written now. They're slightly different in terms of first order flows. The only difference here is that W is defined the same way, but phi dot, instead of being W prime, is some other function S of phi, and W and S satisfy two first order nonlinear equations that I'm not showing you because they're not important. It's important, however, to understand what are now the related integration constants that enter in the equations. Before, for the equation for W, we had one, C, and this was controlling the wave of the scalar. Now we have one more, and this is precisely this dimensionless number that controls the curvature in units of the appropriate coupling constant on which the theory is living on. So the precise connection, of course, to the observables is these relations that I wrote before. This is the appropriate definition I used before, and this is the relation that connects the vacuum expectation value of O in terms of this parameter C that now is a functional of this dimensionless parameter because the vacuum expectation value of the scalar is in fact depending on the curvature. If this number R script R is positive, then I'm describing positive curvature manifolds like sphere or de Sitter, and if it's negative, you describe ADS. Now, let's look a little bit at the infrared limits of such flows. Now, when the curvature of the space of the manifold on which the quantum field theory was defined was 0, then as we found, and as you all know, the infrared points are always the minima of the bulk potential. However, if the curvature is non-zero, the infrared points can be any other point except the minima of the potential. So the flow will end at some value of the scalar that I call phi 0, provided the potential is not, the derivative of the potential is not 0 there. And in this case, when the flow ends, this is a regular horizon, which is similar to the Poincare horizon in standard ADS. And generically, for each endpoint phi 0 for the values of the scalar, there is always a unique solution. If I start from a point phi 0 and I solve for the solution going towards the ultraviolet, then as a function of this phi 0, I will calculate the data of the flow, which is the value of R and the value of C of R that controls the vacuum expectation value of the operator O. Therefore, one can take the endpoint as a way of classifying all possible flows in the case where you have finite curvature. Let me show you the vanilla flows, what they look like now when you have finite curvature. So this is again W as a function of phi. This is a maximum of the potential, a minimum of B, a maximum of B, a minimum of the potential, infrared fixed point, UV fixed point. Now, if the parameter R is 0, no curvature, then the flow starts at the UV, ends up in the IR. However, if I crank up a non-zero R, then the flow doesn't arrive at the IR, but stops somewhere in between. Let's say here. And in this case, W in fact goes to infinity with a branch cut. And therefore, this is where the flow ends, and the ending point is determining, in fact, the data of how much curvature I turned on. If I turn on more curvature, then the flow stops earlier and earlier and earlier, and as R goes to infinity, then the flow ends closer and closer to the ultraviolet fixed point. And this intuition is, as I said already, matching what we expect from standard quantum field theory. An important, in fact, ingredient which gives us the quantitative control of flows and other data in the holographic theory is the on-shell action. So we have to be able to calculate it and control it. And in fact, one can do this calculation and by using the equations of motion and show that the on-shell action, which I wrote as F, depends on a few trivial parameters like the volume of the boundary, the appropriate power of the Planck scale. And then in this particular case, it has two contributions. This contribution is there whenever you have non-trivial curvature. It's proportional, in fact, to the curvature of the boundary metric. And this contribution was always there. It is the standard contribution in theories which are on flat space, A dot times the volume of the boundary. This one is a little bit more complicated because it involves an integral over a lower power of e to the a, e to the d minus 2a. So this is the answer, and it has to be evaluated at the cutoff near the boundary, and afterwards renormalized, etc., etc. Now, this calculation is valid for the sphere. If you want to go to the sitter, basically you have to analytically continue, then you get a minus sign. Before I delve further into this effective action, I'd like to go back to the sitter space and make a detour about entanglement entropy. So let's consider a quantum field theory in d dimensions on a d-dimensional de Sitter space that I wrote here in global coordinates, which is a s to the d minus 1 sphere, which is changing radius from infinity to a minimum and infinity to a minimum and then back to infinity. And this is basically the metric here. And the d minus 1 sphere, I rewrote it here in terms of a single coordinate theta, and I split it basically so that you can see the two hemispheres which touch each other at an SD minus 2. Now, what I would like to do is to consider the entanglement entropy of the quantum field theory, which is living on this space, between the two hemispheres. That is, what is the entanglement entropy of one hemisphere entangled with the other? And these have an SD minus 2 boundary, or if you are in 4 dimensions, this would be an S2 boundary. So this can be calculated holographically using the real Takayanagi formula. And the result, when you do this calculation, which is quite simple, is again a few trivial factors in front. This is the curvature of the Sitter space. And this is the same integral we have seen appearing, in fact, in our on-shell action. In fact, it's precisely, I wrote the on-shell action here, it's precisely this term. So this term is the entanglement entropy in the quantum field theory of two hemispheres, half hemispheres in the Sitter space. It turns out that not only this term, but also the first term has a thermodynamic interpretation. To see this interpretation, what we will do is we will follow Cassini, Huerta, and Myers and change coordinates in the Sitter. So instead of global coordinates, now we put the metric in the Sitter to be the static patch coordinate. Now, in this case, you have a horizon in this metric, as you all know. This enters also into the bulk. And because now you have a horizon in the holographic solution, there is a standard Bekenstein-Hawking entropy that can be calculated from the usual formula. And it turns out to be equal to the de Sitter entanglement entropy I showed before. This was known, in fact, for CFTs, but this is valid also for general quantum field theories. And in fact, now you had so the entanglement entropy now became normal thermodynamic entropy. There is a temperature, as you know, in this case, which is the Hawking temperature, which is 1/2 pi, the curvature radius of the Sitter. And then you can use the thermodynamic formulae to calculate the energy. And the energy, in fact, gives you this formula, and this formula is precisely the first piece in the on-shell partition function we calculated. Therefore, our free energy, in fact, can be written as U minus Ts. And these, in fact, particular pieces, in fact, are the they give a thermodynamic interpretation in the free energy of a quantum field theory on de Sitter, but also on the sphere. In fact, in de Sitter, it is known that the entanglement entropy that we discussed is also the entanglement entropy in flat space over an SD-1, as was shown already by Cassini, Huerta, and Myers. But this is not true anymore. This was shown for CFTs. This is not true anymore for general quantum field theories. I still find surprising that the partition function of a quantum field theory on de Sitter space has a thermal interpretation. So let me now move and come to F functions and F theorems. I will call a global C theorem the existence of a function on a space of conformal field theories, which satisfies the fact that the value on a UV CFT is bigger than the value of the IR CFT. And I will call a local C theorem the existence of an interpolating function, which is a function of something that runs across the flow, so that, of course, the theory, the C changes monotonically and takes values at the endpoints that give the particular values of the C function. Now, in 3 dimension, a global F function for 3-dimensional CFTs were proposed some time ago as the renormalized free energy or partition function of a conformal field theory in the 3-sphere. And in fact, it was checked in many examples that it works. However, when people tried to use it as an interpolating F function, it was shown that it failed. Meanwhile, an interpolating F function in 3 dimensions, which was satisfying the F theorem, was proposed in terms as an appropriately renormalized entanglement entropy across a 2-sphere in flat space. And in fact, now we have a general proof that in 3 dimensions, this is always monotonic. The problem with this proof is that this cannot be extended to higher dimensions. Now, we have seen that the partition function on the sphere contains a piece that is related to entanglement entropy. And we concluded, in fact, that the de Sitter entanglement entropy and the S3 partition function are tightly connected. And we would like to use, in fact, this knowledge and try, in fact, to define more variants of an F function. So to obtain a local F function, we must have a function, which I call a script F, as a function of a parameter R, and this parameter must interpolate, in fact, between the infrared and the IR. And in my example here, R will be precisely the dimensionless parameter that's controlled by the curvature. Because when R goes to 0, I arrive in the infrared theory, and when R goes to infinity, I arrive in the ultraviolet theory. Moreover, at the fixed points of the flow, the function f of r must take the values fuv and fir, which are given by the global f function, which is the appropriately renormalized partition function on the sphere. And then this function has to be monotonic. If I achieve this, then I'm done. The crucial point, though, for this to happen is that I must have a partition function that is finite both in the ultraviolet and in the infrared. And the particular limits that it has to take in the ultraviolet and the infrared, which are the 2 fixed points, are the ones we know that in a holographic theory give us the normalized partition function for the CFTs, which are related essentially to the ADS scale in the UV and the IR CFT. Now, when you start computing the sphere free energy, in general, it's a function of the curvature and a UV cutoff. It is UV divergent when the cutoff goes to infinity, and the detailed structure of the divergence is well known, and we know how to renormalize via holographic renormalization. The free energy is also infrared divergence when you take the curvature to 0, and the most trivial divergence, of course, comes from the infinite volume, but there are subleading divergences. And the detailed structure of the general infrared divergence, in fact, can be determined. And this is what we did in particular for holographic theories. So we know analytically the infrared asymptotics of a generic bulk theory. So then you have to subtract UV divergences by renormalizing in the standard way. And by doing this on a holographic theory NS3, you introduce two arbitrary scheme-dependent constants. Then you have to remove infrared divergences. Liu and Medjay, in fact, did it by using differential operators. There are other ways. In fact, there are an infinite number of ways. But we found only 4 simple, distinct ways of doing that. There may be others, but these are the simplest we could see. And in this way, we can construct, in fact, 4 independent F functions. I'm not going to show you because I don't have enough time. If somebody cares, can look at the paper or ask me later. What is interesting, however, is that instead of starting from the sphere free energy, I can start directly from the entanglement entropy of the setter. And by also removing infrared divergences, normalizing and removing infrared divergences, I can construct 2 distinct F functions from the entanglement entropy that I call F5 and F6. And it is surprising, at least a priori, but after a while, when you realize that the 2 are related, not so surprising, that these 2 F functions are related to 2 of the 4 F functions you construct for the sphere free energy. And therefore, they are not independent. Now, these F functions, you must supplement them with one prescription, that when the dimension of the perturbing operator is smaller than d over 2, then instead of the partition function, you must use the effective action. That is the Legendre transform of the partition function. And then by using this, we have checked many examples, both holographic and also some quantum field theories that can be computed analytically, that these are monotonic. So here I showed you a plot where I took a generic, in fact, 4-dimensional bulk theory with Mexican height potential, perturbing operator of a given value, delta minus 1.2, and I plotted the 4 distinct F functions, which are clearly monotonic between the infrared and the ultraviolet fixed point. And also I have plotted the Singha, Myers, Liu and Medjay example to show you, of course, this is also monotonic, but it's distinct from these. We checked various other things. We changed dimensions, changed potentials, etc. They are always monotonic, at least to all the cases we could check. We have checked also for the theory that made the original proposal of the S3 partition function fail, and this is the free massive boson. But here you have to Legendre transform, and when you Legendre transform, our functions are also monotonic. However, we have no general proof of monotonicity so far. So let me conclude. The space of holographic normalization group flows is richer than perturbative RG flows and allows for several exotic possibilities. Some of them show radical departures from standard perturbative intuition and should be studied further. The black holes which are associated with these exotic RG flows have been analyzed already and exhibit many of the phenomena that appear also in finite curvature case. The definition and study of F and C functions is still an open problem in several cases and dimensions, in particular in 5 dimensions. And I would like to end by saying that the tools we developed seem very useful in order to understand the genericity of Coleman-de Lucia transitions in the ADS regime with surprising conclusions. Thank you for your attention and your patience.
Okay, thank you very much, Elias, for very nice talk, a very instructive talk. So, any questions, please?
I have a question. Can you hear me?
Yes.
Have you tried to, probably you're familiar with analysis of dynamical systems by Conley index. It was a work by Sergei Gukov to analyze renormalization group flows, different exotic energy flows.
Yes, in fact,
have you tried to apply this?
Sorry, yes, go ahead.
No. Have you tried to apply this technique of Conley index and other topological indexes of dynamical systems to all these exotic possibilities?
Right. I had discussions with Gukov on this. In fact, this require basically what we are finding is, you see, this is a set of theorems, topological theorems, that are applying to first order equations. And what we're having here is a more complicated equations, that is, or we project them onto first order equations, but then, as you have seen, there are many places where the second order of the equations, in particular, when bounces happen, that resurges again. Therefore, there is one needs a new formulation of the original system of equations so that this applies to what we're finding here, that is to our equation. We are thinking about it. It's not so obvious. It should be doable, but it requires some thinking and also some mathematical prowess. I don't have anything better to say at this point. It's an open problem.
Okay, thank you.
More questions, please? Okay.
I have a question. Can you expand a bit on the last point?
The Coleman de Lucia.
Yes.
In fact, if you have to remember that if you want to have a Coleman de Lucia transition, you need an instanton. Now, Coleman and de Lucia, by making the thin wall approximation, they were managing, of course, to solve the equations. And that gave the impression that you can find such instantons generically. That apparently is not the case. In fact, the thin wall approximation is probably never valid in the holographic setup. And moreover, if you want to find such instantons, in fact, you need very highly tuned situations, which I didn't have time to show you, but they look similar to the skipping flows I showed you before. That's when you get, in fact, at finite curvature, because you need instantons that are spherically symmetric, not flat. At finite curvature, to have, in fact, solutions which have a moduli space and which flow from a minimum to a minimum. So these seem to be very, very finely tuned. And this is something that Tom Banks, I don't know how, he guessed it, that in fact he mentioned at some point in one of his papers, that this must be very, very rare. That's what we're finding by detailed study of the equations and by understanding the structure of solutions.
Okay, thanks.
So they are not as generic as people thought from the Coleman and de Lucia and others, in fact, analysis.
Yeah, I have one more question. Probably it sounds quite strange, but where to move further? I mean, where do you think it's important to move further here? I mean, for curved space, RG flows. I mean,
there are many problems.
Equilibrium properties or something. Another.
Yeah, there are many problems that, of course, we haven't touched. You start by doing the most obvious and the simple things. I can tell you a few things we are doing, and there are many more others that one can do. In fact, it is by now known that if you consider, in fact, quantum field theories on products of spheres, there are phenomena that, at least for us, were unexpected. For example, if you consider a four-dimensional CFT on S2 cross S2, Of course, you break scale invariance spontaneously. That's not a surprise. But suppose that you take the two S2s to have the same radius. Therefore, the CFT is invariant under a kind of parity-like symmetry which interchanges the two spheres. Well, you find out that in the holographic theory, this parity symmetry is spontaneously broken, number one. Number two, you find that there is an infinite number of Efimov-like saddle points in the solutions. I mean, we can show this analytically, but we would like to understand it better by understanding because we know that Efimov vacua in fact appear when you violate the BF bound. And here we don't have scalars to understand the violation of the BF bound, but there might be some ways by compactifying to map it to this. So these are phenomena that are happening. It is possible that most of these vacua, like we found long time ago with Matti Järvinen, are unstable. We don't know yet because one needs to do more analysis. And there may be even more phenomena, in fact, that could be happening when you have several curved manifolds, in fact, in your theory. We find also that if you take confining holographic theories, in that case, you find two, not one saddle points, and we don't know whether, first of all, what's the observable difference of these points one needs to compute, and whether these things are things that are happening also at finite n and therefore can be seen on the lattice. And as you can imagine, these are the most obvious things. There may be many more things. It's just that rarely we think about quantum field theories. There are many phase transitions, in fact. We found a few simple ones. There may be many others. It's just that we don't usually think about the dynamics on curved manifolds. And I remember when I was a graduate student and I asked once one of the professors, why don't we study renormalization, group flow, and beta functions on curved manifolds? He dismissed it, saying that, look, beta functions come from the short distance properties of quantum field theory, and on a curved manifold, the short distance properties are that of flat space. Therefore, you don't expect a difference. And in perturbation theory, he was right. But beyond perturbation theory, this is wrong. And in holography, we have ways of going beyond perturbation theory. And there you see, so it's what I mentioned before. Curvature is ultraviolet irrelevant, therefore you can study it in perturbation theory if you wish, but it's infrared relevant, and therefore the effects in the infrared you have to calculate using some non-perturbative technique. So it's up to you to think even new things. I haven't thought of everything. I thought of a few obvious things, but there are many, I can assure you.
Mm-hmm. Okay, thank you.
Okay, more questions, please.
I might have a question, which follows up on your last point. So a little bit at least. Can you use these holographic methods to maybe isolate some sorts of classes or groups of flows, which would be unaffected or weakly affected by a changing of the background? So which would look the same as the flat space flows if you put the theory on the curved manifold or something like this?
Well, it depends what you mean by looking the same. As holographic flows, as you have seen, they look different in the sense that instead of going to the minimum of the potential, you start stopping at different points. Of course, this is reflecting the fact that once you have positive curvature, you have a gap. So you have to specify some observable in order, if you wish, to make your question precise. For example, you can ask questions about spectra. You can ask questions about correlation functions. We know cases, for example, I haven't had time to show you because in 45 minutes, there is only a few things, but in our papers and even in some backup slides, I have many plots of different cases. And there are cases, in fact, where nothing special happens when you turn on curvature. But there are cases, in fact, and quite a few, in fact, it's not so uncommon, where there is a very, very non-trivial structure that appears once you turn on curvature. For example, let me show you just one such graph, if I can find it here. You remember I showed you this example of skipping flows with 2 UV and 2 IR fixed points. Let me see. Yeah. So this is the same plot. So if you see here, this is UV1, UV2, IR1, IR2. This is a very complicated, in fact, set of flows, especially when you turn on finite curvature. And many non-trivial things happen here. It's difficult to explain them all, but I'll show you one such example, which is this particular very special point. In fact, here the different colors indicate, as I told you, if you take any value of phi here on the axis, you can start a flow there. Where it goes, you have to work it out to see which ultraviolet point it ends up. That's what we did, in fact, numerically. But there is a point here, which is this phi exclamation mark, which, in fact, if you start a flow here, in fact, well, it's impossible to numerically start a flow there. That's the first thing. But by looking at what happens at the two sides, you realize that the flow that it's impossible to find is precisely one of these flows I alluded to when I was discussing the Coleman-de Lucia story. It is a flow that starts at this IR1 and ends up in this IR2. And it has a moduli space, but you can never get it numerically. You can find it indirectly by approaching it from two sides. But this here already, you can see other phenomena, for example. Here you see a case where this is, in fact, on this axis is R, this dimensionless curvature. You see there is a point in the middle here. You are not at the UV fixed point, but the curvature goes to infinity. According to what I told you, this doesn't make sense. I should have had a fixed point there. But this is not, in fact, a fixed point. This is a point where the bare ultraviolet coupling vanishes. And that's why this R goes to infinity. So this is a different saddle point of this quantum field theory at finite curvature. So this suggests that you have a conformal field theory and it has two saddle points. One saddle point at finite curvature has 0 VEV for the scalar, and the other has a non-trivial VEV and a moduli space for the scalar. And this also, it appears generically, in fact, in the de Sitter slices. So there are many such phenomena, and I don't think I understand the general structure.